So I'm going to talk to you guys about pulsars and generally what I do as part of my research at UofT. So what is a pulsar? Usually when you want to find out what a pulsar is, or when you want to find out what anything is, what do? Your first instinct is to Google it. And you do. Don't laugh, it's right down there. Google, as usual, knows what a pulsar is. Second thing you do is you look it up on Wikipedia, because you want to know what it is as opposed to just having a pretty picture of it. And Wikipedia gives a brilliant description. It goes, a pulsar is a highly magnetized rotating neutron star that emits a beam of electromagnetic radiation. This is a very dense description, but it is an accurate description. And we're going to go through it. And hopefully by the end of this talk, you'll know what a pulsar is, and also what we do with them and what I do with them in my work. So the first part is that it's a neutron star. What is a neutron star? Here's a life cycle of a star. First, you start off with a stellar nebula, which is just a gas cloud, which collapses to form either an average-sized star or a massive star. The average star is like our own very sun, which becomes a red giant and ends in a very boring white dwarf phase. The massive star, on the other hand, explodes in a supernova and can form a black hole or a neutron star. When it forms a neutron star, that's when I start looking at it. So just for you guys to calibrate how big a supergiant is, this is Betelgeuse, and it's a red supergiant. It's about 900 times bigger than the sun. And there's the little sun, and there's Betelgeuse. And for those of you who might be going upstairs to see to use the telescopes, I mean, you might not because it's really cloudy right now. But if there weren't any clouds, that's where Betelgeuse is. It's in the Orion constellation. All right. So we talked about how the neutron stars are born. You start with this red supergiant. It explodes in a beautiful supernova, and it leaves behind a neutron star amongst a massive nebula. How do we know this, though? It's because we've seen it happen. There's a very particular pulsar that some people at UofT do study called the crab pulsar. This is an image of it where it's a false color image where the red is the optical observation and the blue is the X-ray observation. But it sits in the center of a massive nebula called the Crab Nebula. And this picture is taken by the Hubble Space Telescope. And one of the cool things about this nebula is that we've been observing this nebula for a very long time. And at some point in the 20s or the 30s, people noticed that it was expanding slightly. And they worked backwards and said, if it's expanding this much today, how big or how long ago did it actually explode? And they worked their way backwards, and they discovered that somewhere around the year 1000 is when this supernova had to have gone off. So then they went through the historical records, and they found out that yes, indeed, there was a supernova in the year 1054, where Chinese astronomers wrote it down, and someone rudely highlighted over an ancient text. And the Europeans drew a very awesome painting with a guy pointing at the star, marveling at the fact that there's a new star in the sky. All right. So how big is a neutron star? To give you a comparison, it's about 20 kilometers wide, but that doesn't really help you much. 20 kilometers, you drive in it, but you don't really see it from outside. So here's a comparison of a neutron star versus Toronto. You're right down there by the red dot, and centered on that dot is a 20-kilometer wide circle sitting on Toronto. And that's how big a neutron star would be. Now, a neutron star usually has a mass somewhere between 1.5 times the mass of the sun to 2 times the mass. And all of that gets compressed into this tiny volume that would sit inside a mid-sized North American city. So that's very dense. And one of the things that you all might know, that when you have something very heavy, something that dense in a very small area, one of the effects you get is that gravity is very strong around it. Now, for those of you who are not familiar, these are the 4 fundamental forces. We're going to keep revisiting these over time, because one of the things that neutron stars or pulsars that is interesting is that they're one of the few unique objects in the entire universe where all these forces are observed in a very dominant way. Most places you just see the gravity or you just see the electromagnetism, but here all 4 of them. So the first one is gravity, that you have this compact object, very massive, very small, and gravity is extremely terrifyingly huge around it. If you were to stand on a neutron star, you would be instantly crushed into a pool of carbon, basically, about 5 micrometers thick. All right, so what's inside a neutron star? Here's a very simplistic diagram of a neutron star. And the outside is the crust. It has something very simple. It just has ions and electrons. It's very thin, not very interesting. In the inner crust, these things start crushing into more denser materials like electrons, neutrons. We call it nuclear pasta because they form these spaghetti-like structures. Actually do. And that is the technical term for it, by the way. You will find papers on nuclear pasta. And as you go further, sorry? Oh. And one of the cool things here is that all these neutrons and ions and whatever was outside in the universe is being crushed, and it's decaying into these neutrons as far down into the neutron star you go. And this is caused by the weak nuclear force. Now we're not going to explain all these forces in extreme detail because they're just highly complicated, and actually I don't know what like the technical details of what the weak force is, but it's there. As we go deeper into the neutron star, you reach the outer core, which is mostly just neutrons, which is good. That's why we called it a neutron star. But the inner core, what is that made of? And that's the big question. We don't know. We think, we have theories, we have many models of what it might look like. We know it has something to do with the strong nuclear force because it's this regime of physics where everything is super ultra dense, where everything is on the border of being a black hole. You add too much mass to a neutron star, it's going to collapse into a black hole, and this is on the border of it. And so we don't know what that looks like, and that's one of the general problems that we're trying to solve. So just to summarize, understanding what the core of the neutron star, the part on the diagram where I had all the question marks, will lead to a lot of interesting new science because it'll tell us about what materials can even exist. We haven't seen these materials before, and we can't even envision them. We have so many models, but we have no confirmation. To do this, though, we just have to measure the masses and diameters of neutron stars very precisely. Sounds simple, but it actually isn't. Just, how heavy is something and how big it is. But because neutron stars are the size of like 20 kilometers, imagine a 20-kilometer ball, light years, parsecs away. It's very hard to actually look at it and find out exactly how big it is. But this is pretty much what most pulsar science is about. All right. Let's go to the next part. A pulsar is a highly magnetized rotating neutron star. So why do they rotate? Most neutron stars do actually end up rotating, and there's a very simple physical reason for it. Here's a video by a silver medalist figure skater. And you see he makes himself big, and as he pulls his arms in and becomes this more compact object, it starts spinning a lot faster. It's just a general thing that happens to everything. For those of you who get really bored in offices, you spin on your office chair and you pull your arms in, you start moving faster. That's pretty much what I do as part of my work here. All right. How fast do the pulsar spins, though? The fastest pulsar we've detected so far rotates 716 times every second. This means that if you were standing on the surface and somehow surviving, you would be traveling at 24% the speed of light, which is about 21,000 kilometers per second. I would really love to put this into some physical terms, but there are none. There's no intuitive way of understanding how fast this is. If the Earth was moving that fast for you to be traveling at 25% the speed of light, a day would last half a second. It would be spinning twice every second. That's how fast the Earth would have to spin. That would never happen. The Earth would tear itself apart and it would explode and everything. But if you want to understand how fast 716 times every second is, I did some top quality research last night, and I found out that one of the fastest blenders in the world is the Vitamix Turbo Blend VS, and it only spins at 617 times every second, which is abysmal compared to the 716 here. Yeah, makes a great smoothie though. Last part. It's highly magnetized and emits a beam of electromagnetic radiation. I've highlighted them together because they're pretty much the same phenomenon. Where you have this model, and I know it's a very intimidating model because it's just diagram, scientific diagram, something you would see on an exam if you were in college. But just very briefly put, a neutron star has a magnetic field, and the magnetic field just accelerates these charged particles near its poles up there and here, and that just causes this beam of radio waves that you see. And this magnetic field is extremely strong. It's like 100 million times that of Earth. Earth has a pretty good magnetic field. You know, you put a compass down, it tells you where north is. This would do a lot more than that. But that's our final force. And the reason I tell you this is because it really is one of the few unique objects in the universe where you actually see all four of these. And you can study all four of these and how they interact with each other and how they don't. And it just forms this natural laboratory that's given to us that we need to look at more closely and learn a lot. All right. So how do we look for pulsars? We point some sort of telescope up to it, and we call them radio telescopes. There's Arecibo. Until very recently was the largest radio telescope. It is currently the largest working telescope in the world. The one that's bigger isn't actually working yet. And on the side there's Effelsberg telescope, which is something that maybe most of you might recognize more as an antenna that moves. Arecibo doesn't move, it's stuck to the ground. There's that hanging thing that actually moves around. It's like the opposite of what you would expect. But that's cool, you know. But I would like to show you what we actually see in the radio telescopes when we point it at a pulsar. So here's a schematic of a very simple pulsar. You know, it's spinning. But we don't actually see this part. This is just a drawing we make. We infer that from what we see. What we really see is just this little, you know, this little peak here. And it happens every now and then. Every so seconds you will see that peak. And it's very periodic, it's very precise. And we see that, and over time we figured out it's really these neutron stars with those beams coming out of it that's spinning. Now I'll give you a better example. Now this video is going to have sound to it, but you know, pulsars don't actually make sound. This is just me having taken the data we have and I just made it go out of the speaker. But that's pretty cool. Here. Apparently I forgot to connect the sound thing. Oh, there you go. Yeah, you all hear that? Awesome. So that's what you would hear if you put this through a radio, really. I mean, the pulsar doesn't make sounds, but it does emit radio waves, which means that if you took your run-of-the-mill radio and you traveled near a pulsar and you turned on the radio, you would hear that from the radio, because pretty much the same principle. Here's another one, more exciting, it's faster. There you go. Yeah, I would let it go on, but I have a talk to give here. Awesome. So let's go through a short history of pulsars. You know, I've told you what a pulsar is. I hope everyone understands what a pulsar is. But how did we come to know this, and how did it all begin? One fine day, November 28, 1967. Almost exactly 49 years ago, actually. The first pulsar was discovered by Jocelyn Bell Burnell, working under Anthony Hewish. And that was actually their actual observation, where they just had this tape recorder sheet with a bunch of pulses on it. And they didn't actually understand what it was at first, but eventually they figured out that it was a pulsar, and there's a little note there, modest note, first observation of pulsar. But before they figured that out, they thought that they were extraterrestrial signals, which is why it was nicknamed LGM-1, for little green men. Unfortunately, it's not an extraterrestrial signal. That would be cool, though. All right. After we discovered the first pulsar, a few years went by, and people discovered the first binary pulsar. This is a pulsar that's orbiting another neutron star or white dwarf, and it has some interesting properties. It was discovered by Hulse and Taylor, and here is a video of that. And as we watch this video, you can see that they're orbiting each other, but Einstein came up with his theory of relativity. And in that theory, he told us that all orbits eventually decay. And you see, they're decaying, they're getting closer to each other, and they're starting to spin faster and faster and faster and faster until, you know, one day they merge. There is a part after this video that I cut out because, you know, spoilers. Also because we don't actually know what happens after this, so it felt a bit unscientific to leave it in. But for the most part, it will create a black hole. It will destroy both neutron stars and they'll coalesce into a black hole. There are some cool YouTube videos about it. Awesome. So what do we do with this? Well, the first thing that was cool about this discovery is that we could actually test Einstein's relativity, because this behaves exactly as he said. So we have Newton, who said, you know, the orbits will always stay the same forever. Something's orbiting something else, it's going to do that forever. And that's that line that Newton's theory predicted, the line of zero orbital decay. And Einstein comes along and says, no, they will decay, and they will decay in this exact specific manner. And there's that curve predicted by Einstein. And guess what? The measurements actually line up almost perfectly. This has error bars and everything, all the uncertainties, all the problems taken care of, and they fall on the line almost perfectly. Here's the point where they won a Nobel Prize for that. But we kept looking to make sure that they were still right, and it does follow through. And we expect it should follow that curve perfectly until they eventually form into a black hole, which will be a long time later. This is really cool. You can use pulsars to prove theories of gravity. All right, what happened next? We discovered a double pulsar. This is really cool. It's the only one that we've discovered, even today. 2003, we discovered 2 pulsars in an orbit around each other. Normally, you see a pulsar and another neutron star that's not really pulsating to us, but here both of them were pulsating to Earth, and you could see both the pulses at the same time. And they're orbiting really close together. They're orbiting at like 7 hours or something like that. So imagine these 2 ultra-dense balls that are pulsating giant energetic beams of radiation spinning around each other really, really fast. And you can do some cool things with that too. Yeah, there's a scary diagram again, but don't worry. The main thing I want you to get from here is that there are 5 different tests of general relativity that predict different masses for what these pulsars will be like. 5 different. These are independent. And it's amazing how well they agree with each other. We have to magnify this little spot by 80 times before you can even see where they actually intersect. That's how accurate this is. So main point of this is just to tell you that, you know, when we could use pulsars to show that Einstein's relativity works really well. And this is one of the iconic plots to show that. If you guys want to know what the lines mean, you can come after the talk and I'll explain them to you. But yeah, since that very first pulsar in 1967, we've discovered over 2,500 pulsars. And every year we build more radio telescopes, bigger ones, better ones, more expensive ones. And the number is going to rise faster every year. All right. So what other crazy types of pulsars are there? There are a lot of them, but I want to tell you about my personal favorite, because this is the one that I work on. And it's called the Black Widow pulsar. It's a binary pulsar that slowly destroys its companion. And there's a photo of what it's named after, the Black Widow pulsar. Sorry, the spider, yeah. But yeah, so the Black Widow spider is famous for, well, cannibalizing their partners. And that's what the pulsar does too. And I have a cool video for that too, from NASA's Flight Center. Here's the pulsar spinning, and its pulsar wind is like a blowtorch to that other star that you see. And it's just destroying it over time, it's just blowing all that gas away. And there's nothing really to say aside from it being super cool. Here's an aerial view of it, if you like. You can see the pulsar from above, and it's just blowing the outer layers off the star right beside it. And over time, it's just going to destroy the whole thing. But yeah, this is a really cool system because they do some cool things, such that Black Widow pulsars tend to be heavier than other pulsars. Remember way back when I told you that we like knowing the masses of pulsars? Well, these pulsars tend to be heavier. They tend to have more mass. And it helps to know what's the heaviest pulsar you can detect, because the heavier you can go, the further you can push the boundary, the more you can learn about the theories and what possibly creates a pulsar. So sort of think of it as an arms race and trying to find the heaviest pulsar. Like whoever breaks the record wins a prize. They do. All right, but will pulsars ever be useful to people, you know, like you and me? Note, I didn't talk about pulsar science. Pulsar science might actually end up being useful, the things we learn from pulsars. But will the objects themselves ever come to use? And yes, they will. We've already sort of used them when we sent out the Pioneer and the Voyager plaques, where the goal of these plaques were that back in the day, they hoped the extraterrestrials would find them. And they sent this map along with it. It's a map of the sun, relative to 12 other pulsars. And every line has these little dashes and dots, which signify the rotational period of a pulsar. In a galaxy where you have thousands, maybe millions of pulsars, and each one with this very unique frequency, and each one orbiting at a very precise amount of, like, they're very precise. They're sometimes more precise than our most powerful atomic clocks. And if you have a good map of all of these, you should be able to navigate across the galaxy just by knowing the different pulsars, and you can calibrate where you are based on what you see around you. So this was the first sort of manifestation of that, where we tried to send out plaques that would hopefully one day tell extraterrestrials where the Pioneer and Voyager's probes came from, because they can use this map to find where we are. And it's being used currently in this mission that's going to be sent out early next year, called the NICER mission, which will investigate the viability of pulsar-based navigation. Another cool thing about this mission is that it's going to fly up to the International Space Station and just plop down on it. It's not going to be orbiting the Earth or anything. It's actually just going to climb down on the International Space Station, which is one of the first times that's going to happen. So it'll be really cool. But yeah, imagine maybe 500 years later, where we are a Star Trek race, you know, with warp drives and everything, spaceships. We might actually be using pulsar maps to navigate, find out where we are and where we're going. That's pretty much the only use I could find for pulsars, by the way. So that's it. All right, what do pulsar researchers at UofT do? People like me, people like some of the few sitting in the audience. Now this part is going to be a bit complicated, because honestly we don't know what we do, but I will try to explain it the best of my ability. There's this thing called sentallometry, and it's sort of a play on words between scintillation and astrometry. But scintillation is when stars twinkle. You know, you look at the sky and there are these atmospheric effects in the sky, and they cause stars to twinkle, and we call that scintillation. And something similar happened with pulsars, where you look at faraway pulsars and there's the whole interstellar medium, all the gas between you and the pulsar, between the Earth, between the solar system and the pulsar. And that gas causes a similar scintillation. It's a lot more complicated than the scintillation that we see with stars, but the principle is the same. Yeah, sentallometry is the study of pulsar scintillation due to the interstellar medium. But here's a diagram to help you understand that. Here's the pulsar, and here the Earth is. And here's some sheet in the ISM. Just imagine some weird structure. And it deflects light, you know. As you all know, the speed of light is constant, which means that this signal that goes straight to Earth, I'm having trouble moving my laser pointer in a straight line, but the lines that go straight from the pulsar to the Earth, they arrive faster, and the ones that deviate and then they get bounced back into Earth, they take a longer time to get here. And you can sort of analyze this signal, and you can recreate what you're seeing. In a sense, to make it, you know, to explain it, we can use this ISM sheet as a massive naturally occurring lens in the sky. You know, normally to do good science with pulsars, we would have to build enormous radio telescopes, you know, 500 meters wide, maybe a kilometer wide in 10 years. That pales in comparison to how awesome these lenses will be once we learn how to use them. We estimate that the lenses on these sheets will be on the order of like 1 AU. So imagine a radio telescope the size of Earth's orbit around the sun. And that's what we are just given naturally by the galaxy and its interstellar medium. And the hope of the study is to use that as a meaningful lens and look at the pulsar behind it. And really we're just going to use it to, you know, find the mass and the radius of the pulsar, which is actually sounds more boring than it really is. But yeah, giant lens in space. If anything you take away from this sentallometry, it's a giant lens in space that we use to look at things behind it. And when you look at the signal that you get from a pulsar that goes to the sheet, we get some data, and we make something called a dynamic spectrum. Now, main reason this slide exists is just because it's pretty, and I wanted to show it off. There. That's what it actually looks like. This is a simulated spectrum. This is the observed spectrum. And this is in time. So they observed the pulsar for about 1.5 hours. This is spectroscopy. They just looked at different frequency, different colors of light. And it forms this awesome pattern. You know, it's bright here, it's weak there. And it forms this wavy pattern like, you know, you would see in a swimming pool. And it's really because you have these waves and the turbulence in the ISM, and it's refracting light or diffracting it in funny little ways like this. And if we understand what these mean, we can use the ISM as a lens. And we can look at the pulsar in resolutions that would have been thought to be impossible 10 years ago. But this is what we try to do at UofT. We haven't done it yet, but we will one day, hopefully. So in summary, there's 3 things I would like you guys to take away from this talk. One is that my initial title up top was true, Pulsars are extreme, ultra-dense material that spin dizzyingly fast. And dizzyingly is an understatement when you really look at the fastest spinning pulsars. Second thing is, pulsars are unique laboratories where all 4 fundamental forces play an important role. This is almost never seen anywhere. The only other place where you see all of these play an important role is the Big Bang. And it's really hard to go back there. Not difficult, not impossible, but we can still look far away. We can do cosmology and stuff like that. But to have an actual object that's tiny and you can, play around with it, that's a whole different ballgame. And the last thing is that pulsars are cool, I mean, that's the most important part for me, is the whole reason I do it. And none of the other slides matter, it's cool. So that's why we do this. Anyway, questions? Is there a process for this?
Yeah, you can go and pick someone if you've got any questions.
Go ahead.
In the crowd.
Why is the magnetic axis not at right angles to the electromagnetic waves?
Let's see if I'm correct. You're talking about this slide? So what was the question again?
Why is it not at right angles to the radiation?
Because the radiation, well, there is no real reason for it to be. What the magnetic field lines do is that they accelerate particles along them. You have an electron that comes buzzing around, it hits one of the lines and it accelerates along the magnetic field line, which causes it to release a photon.
I guess I'm thinking in a light wave, I believe that it moves perpendicular to the radiation, so I guess I thought this would work.
Yeah, but radiation is an electromagnetic wave. It's both of them together, so it can be in any direction. Yeah, the directions don't matter. They don't have to be at right angles. Yep?
How do you measure the decay rate?
So the decay rate, the way we measure it is that...
Is it an objective measure, or is it something that I can, fit any line on if I wanted to measure in different ways?
What do you mean?
Are there many ways to measure the decay rate, or just one measure?
Well, there is only one measure, because really what you're measuring is every orbit has a time, right? Let's say they orbit, in 7 hours they complete one orbit, right? And then the next orbit takes, let's say, 6.99 hours. So we're really just measuring that time of how long every orbit is, and it goes down over time.
The difference between the times?
Yeah, that's the shift of the orbits. Yeah. Yep.
So with the pulsar and the animation they had, there were pulsars like 2 ends of the pulses that were with radiation coming out. In the animation, I think that one, only one of the poles actually hits us. The other one goes below us.
Yeah.
So is it possible how would that work? And would it make sense for a pulsar for both the poles to hit us?
Yeah, so that's what the double pulsar is. This is a really bad photo, honestly, because it's not supposed to be taken from Earth's perspective. But the double pulsar are the 2 neutron stars where the beam crosses over our line of sight. And the binary that you see here, this one it has a pulsar which crosses along our line of sight. And the other neutron star might also be a pulsar, but we can't see it, right? So pulsars aren't like different objects. They're basically neutron stars. We just call them pulsars because we see them pulse, right? So pulsars happen to be neutron stars that emit a beam of radiation and just happen to be spinning like that, right? But if you see a random neutron star, it might not pulsate to you because its beam is missing, right? But at that point, you can't really tell the difference, right? So
single pulsars, how would that orbit work where only one beam hits us and no one misses us?
So you're talking about sort of this video, right, where you only see that one peak? Yeah, most of the time you actually see two, but sometimes the other will miss you. And the reason this is important is because if we had shown an animation of where both the beams hit the eyes on Earth, then I didn't want you to get the idea that that always happens. You know, sometimes you just miss a line and you only see one beam. You know, it sort of grazes by. Yeah.
Back in the photo where you showed the gas giant coming down and forming a neutron star or a black hole.
That one?
I think one before. Yeah.
Yeah.
There. So what's happening with the black hole? The gravity field's kind of separating and the neutron star is...
This isn't, both don't form. This is like a flow chart sort of. Either the neutron star forms or the black hole forms.
Oh, okay.
So it's not both of them, yeah. So depending on how big your supergiant really was, if it's enormous, you'll always form the black hole. If it's slightly smaller, like Betelgeuse, where it's like 30 to 10 solar masses, then it'll form a neutron star. But this is sort of just a map, right? You don't form both the objects and the fork.
A good question. In our Milky Way black hole, as we pull in particles to make a mass in the center, what's going to happen with that mass? Is that at some point the black hole is going to lose gravity and that's going to allow those particles to freely float out? Or I get the feeling that black holes trying to eventually do that and make a bunch of more neutron stars? I'm not sure.
Black holes will stay black holes for the most part. It's just the end of the line for stellar death. Once you form a black hole, you just stay a black hole. Nothing really happens after that because everything's stuck within an event horizon. But that is a complicated question, so you can come up front and ask me at the end. Yeah. Yeah.
When the first pulsar was discovered, what does that mean in layman's terms? Like, what did somebody detect?
Yeah, so people had theorized that neutron stars exist for a long time, but we hadn't actually seen them, right? When I say that Jocelyn Bell discovered the first pulsar, that was the first time we had actually pointed a radio telescope at one and actually seen the pulses and actually proven that it exists. So that's the first time we actually observed it. So that's what we call, we would consider that sort of the discovery.
Pulses, that's what.
Yeah. Yeah?
What's the average temperature of a neutron star, like on the surface?
I actually don't know that. I didn't look this part up. Where's Dana?
So they might not actually be cool.
Oh no, they're pretty hot. Yeah, they're really, really hot by our standards. I just don't know how many millions it is. It's definitely more than a million, but I don't know the exact number. Yeah?
So a little over a year ago, we had the discovery of the gravitational waves shortly after they turned on LIGO.
Yeah.
They were talking about when they upgrade the system, they will be able to detect, they were saying they were going to see merging of black holes on a regular basis. And there was also discussion at the time about these binary pulsars merging. Actually, I don't know if it was binary pulsar or just binary stars.
Just neutron stars. Yeah.
Neutron stars. So, talking about the merging, the video you showed there.
Yeah, so
Let me just finish.
Yeah.
So your particular study is on the Black Widow version of this. Are you going to be able to make use of the technology from these gravitational waves, or are they going to be insensitive enough for what you need?
Well, the Black Widow pulsars are not going to coalesce or merge within my lifetime anyway, so we can't really use it for that. The outburst of gravitational waves that you're talking about, they happen at the end of this video where it merges and it just forms a big black hole. So for most of the binary systems we observe today, that's going to take thousands of years for that to actually happen. So when that happens, you'll detect gravitational waves. But the Black Widow pulsars specifically are not going to do that. Also because they're not orbiting another neutron star, they're just orbiting a very low mass dwarf. So you know the video in which the star that was getting blasted like a blowtorch? Right. That's not another neutron star, that's just a very low brown dwarf, slightly heavier than Jupiter really. And so that won't create much of a bang. Yeah. More? Okay. I think someone back there. Oh, okay, yeah.
You showed a picture of a pulsar rotating, a star rotating a pulsar that is taking the mass of the star. What happened to the planets of that star?
Well, if there were any planets around that, they're getting destroyed completely. Yeah, they don't exist anymore. But it's unlikely it had any planets to begin with, but I don't really know. Yeah. Yeah. If there were planets, they're likely destroyed by now. Because that's a very violent reaction. Yeah?
What's the nearest pulsar to us?
Sorry?
What's the nearest pulsar to us? And you name them, just calling them pulsars.
So the one that's actually nearest doesn't have a cool name. It has just a coordinate name. It's like 500 parsecs away. It's not that bright. It's really boring. It's slow. It's really, really slow. But yeah, I don't actually know the name off the top of my head, but I can find it for you. Yeah. Yep.
Would a strong pulsar be a magneton?
So when you have a pulsar or neutron star that has an insanely high magnetic field, that's what we call a magnetar. I would have talked about them, but yeah, there's only so much you can talk about. This is going to be my field of study for 4 years, and I'm trying to distill it into 40 minutes. But yeah, magnetars are very interesting. There are people who study them. There's one at the center for a galaxy which gets a lot of interest. But yeah, it's a very powerful, poorly understood object.
Last
Yeah.
What would eventually happen to a pulsar? Because it's giving out energy from the pulsars, would be running out of energy?
Yes. So that's one thing I didn't mention directly, but it spins, let's say you have a pulsar that spins really, really fast. And because it's radiating away that beam, it's slowly losing its rotational energy, and it spins down slower and slower and slower until eventually it just becomes a very slow rotating neutron star that doesn't do much. It becomes effectively inert or, quiet. Well, nothing's ever stationary, but once you get down to that level of rotation where it doesn't have enough energy to even radiate and its magnetic field is suddenly weaker, it'll just stop radiating the beam, or it will radiate very, very weakly and we'll just stop seeing it. But yeah, it does radiate away its rotation and it will slow down.
In a sense, it's not actual material, it's ionized material, right?
Sorry?
It's not actual material, it's not physical material, it's all electrons and ionized first, right?
Yeah.
So you don't really have any mass to go with it. Would it lose mass and there'll be nothing in there?
No, there is mass. The electrons and neutrons and protons are, they
Would it not just go away because of the energy being dispersed off?
no, because they're still gravitationally bound. They're still a star,
I think we better call it there for now, but let's give Nikhil another hand to thank him.
They're at the end.
Before I let you go, I'll just make a few last announcements for the night. Don't leave us now because we have a lot going on after the show. First of all, thanks to our volunteers. But I'd like to direct you to the site where we have information about where to go for other events, including the telescopes, a virtual reality demonstration, and a telescope that's virtual that you can control with your body. We also, as usual, have our planetarium shows. If you're signed up for the 9:15 or 9:30 shows, you can meet Adib and Catherine. One of them will be your volunteer. They're back there in the red shirts. We do also have tickets available for the later shows tonight at 9:45 and 10 p.m. Elisa will have those tickets outside the room behind the doors, so be sure to grab one if you're interested in checking out our show tonight. Otherwise, I ask you to please fill out your feedback forms that you got on the way in, and have a good night.
They're allowed to come up.